Okay, then I'll start. Thanks for the invitation. It's an honor to speak here. So today I will tell you about deformation inequivalent symplectic structures and Donaldson's 4-6 question, and I'll tell you again what this question is. And this is joint work with Amanda Hershey. I'll go through background and history of this problem and give you our results, and then give you our counterexamples and the proofs. So let's start. As many of you know, a symplectic form is let's say closed to even dimensional manifold is a closed and non-degenerate two form. And then we say two symplectic forms, two symplectic manifolds are deformation equivalent if there exists a diffeomorphism, say from Y such that the pullback of the symplectic form has a path to the other one. So this is through path of symplectic forms. Note that I don't require any constraints on cohomology classes. Okay, so the question, a credit to Donaldson, I learned about this in McDuff-Solomon's Introduction to Symplectic Topology book, is that given two closed homeomorphic form manifolds, symplectic form manifolds, are X1 diffeomorphic, are X1 and X2 diffeomorphic if the product manifolds X1 cross S2 with this symplectic form, that's just the product symplectic form, which means that I'm taking the symplectic form from S1 with the standard, X1 with the standard symplectic form on S2. Are these deformation equivalent? So we call this process of taking a product and taking the product symplectic form, taking product with S2 and taking the product symplectic form with the standard symplectic form S2 stabilization, at least in this talk. This is, I guess, in contrast with the smooth stabilization, which is kind of just something with S2 cross S2. So some remarks. Why is this, first of all, why does this question even make sense in the smooth category? We have by wall that two closed, simply connected, homeomorphic form manifolds are H-covariant. And once you take these two simply connected the question in McDuff-Solomon didn't require simply connected X1 and X to be simply connected. And then indeed, if you require the simply connected condition, this is called the stabilizing conjecture that I will state on the next page. But let's just, let's just assume our manifolds are simply connected for now. So two closed simply connected homeomorphic form manifolds are H-covariant. And now if we take cross S2, we're in the dimension squared equal to 5, then two closed simply connected and manifolds. If they are H-covariant, then they are diffeomorphic. So at least for simply connected manifolds, this stabilization will turn our homeomorphic but not necessarily diffeomorphic manifolds into diffeomorphic 6 manifolds. Then we can further consider whether their symplectic forms are deformation equivalent or not. Any questions? Okay. So maybe a bit of history. This was considered at first by Ron. He showed that homeomorphic, there exists example of homeomorphic but not diffeomorphic Taylor surfaces. One of them is CP2 blow up 8 times. And the other one is the Barlow surface. So this is I guess the first example is supporting the conjecture that, so these are non-diffeomorphic, and then when you cross them with S2 so when you stabilize them, they remain non-deformation equivalent. And in their 1997 paper, first of all, they stated the stabilizing conjecture, which I mentioned before. So this is restricted to the simply connected manifolds, asking, okay, I'll just repeat it. If two closed form manifolds are homeomorphic, if you're given two homeomorphic closed symplectic form manifolds, whether diffeomorphism is equivalent to their stabilization being deformation equivalent. And then they show that this is shown for rational elliptic surfaces. Meaning that given two non-diffeomorphic, given two homeomorphic rational elliptic surfaces, they construct symplectic forms on them so that the 6 manifolds remain non-deformation equivalent. And then Yono-Parker also showed this for EN using slightly different methods. I want to emphasize that both of these use Gromov-Witten theory. And in contrast, we actually use a more elementary deformation, symplectic deformation invariant, which is the friction class. And I'll go over that in a bit. And another development around that time was the paper by Smith. He showed that given an integer greater than equal to 2, he constructs and symplectic structures whose friction classes have different divisibilities. So in particular, this implies that Donaldson's question cannot be replaced by T2. So if the product is replaced by anything with 0 friction class, then you automatically get that their stabilization remain non-deformation equivalent by this friction class invariant. So yeah, this is a bit of history. And our result says there exist infinitely many pairs of closed symplectic form manifolds that are diffeomorphic. Well, if you take the product, the symplectic forms remain, they are non-deformation equivalent. So this is a counterexample to the forward direction of I guess it's false. So here we actually give 2 types of examples. So note that for this theorem, right? For this theorem, we didn't require simply connectedness, but our two types of example includes both simply connected and non-simply connected examples, and that still makes sense for us because we assumed our four manifolds are diffeomorphic to start with. So one example is given by, this Smith. So this example above, we actually explore his examples for a little bit more and found that even if you stabilize with the S2, they still remain non-deformation equivalent. And another type of example is given by McMullen-Taubes. I think it was 99 or also around that time. So this is the further example in their paper, which is actually not simply connected. Okay. And then once we show that one stabilization does not make your symplectic form's deformation equivalent, we may ask if we take more stabilization by this S2 and product symplectic form, whether that will stabilize your manifolds at least. And at least in the examples that in theorem A, meaning the Smith and Taubes examples, they remain non-deformation. They remain deformation inequivalent when stabilized with any copies of S2 and the standard symplectic form. Okay, maybe some questions before I. Okay, maybe the theorem statements are clear. So let me give you some motivations and the proof strategy. This is really the most natural strategy you would think of. So you want to find examples of a fixed, smooth, or manifold X that emits deformation inequivalent symplectic structures, omega 1 and omega 2. And then we want to show that their stabilization is non-equivalent. Their stabilizations are non-equivalent. And the invariant, as mentioned before, that we use to show that they're non-deformation equivalent on the sixth manifold is the first-gen class of the symplectic structure. So maybe a bit of review. Given a symplectic form, we may find a compatible J. And there's a contractible, the choice of compatible J is contractible. And then given this J, we might consider the tangent bundle with this almost complex structure, and then we can take its first-gen class. And since like I said, the choice is contractible, we may conclude that for any two homotopic J's, the C1s are the same. So once you consider orbits under diff, of C1, this is a symplectic deformation invariant. Because our definition of symplectic deformation invariance requires you to consider all diffeomorphisms. Okay, so now the goal is to show that for us, at least, it will be sufficient if we can show that C1s lie in different orbits of diff of X cross S2. And a bit more of a motivation before I go into the proof. So we want to emphasize that before us, there are already examples of closed smooth form manifolds admitting symplectic structures whose C1 lying different orbits of diff. And in fact, we use these examples. And our job is to go from 4 to 6. So how do we do that? First, we observe that we will be done for diffeos of x cross S2 that split. So I'll explain a bit more what we mean by this notion of splitting of a diffeomorphism. And we want to constrain. So in order to understand splitting, we want to constrain how an arbitrary diffeo of x cross S2 can act on the second cohomology. So the point is x cross S2, especially for our examples, are pretty easy to understand. Like the diffeos are, we can understand them. And then we can see how first-gen classes, we can leverage the fact that we know that first-gen classes lie in different orbits on the 4 manifold to say something about their orbits under the 6 manifold. So this observation leads naturally to the following definition. So this observation. Given 2 manifolds, X and Y, so this doesn't even necessarily need to be 4 manifolds. We let GXY, we define GXY to be the set of homology equivalences. So this really means maps that induce isomorphisms on cohomology. So we should probably call it cohomology equivalences, but I'll call it homology equivalences for now, such that psi pullback maps the second cohomology to itself. So this is just look, if I restrict my attention to this vector, I want to say the second cohomology is pullback to as the second cohomology of X itself. And then I want to require the projection of psi to the first vector is a homology equivalence. Or okay, and then I define the define gxy tilde in gxy to be the H group of homotopy equivalences. And this means that I replace all the homology equivalences with homotopy equivalences. So this will be needed for the Smith example. They're both useful. Both definitions are useful for us. And a good thing for our example, like I said before, is that both types of our examples have their diffeomorphisms satisfying these type of algebraic conditions. And you can think of it as saying something about that your diffeomorphism being split. And the steps reviewed are, first we want to find a smooth form manifold X with symplectic forms such that their C1s lie in different orbits of diff. And actually, this is not enough. We want to say, we need a bit stronger. We want to find examples so that they lie in different orbits of homology or homotopy equivalences. And then we want to show that their C1s lying, we want to show a proposition that says if the C1 on the 4 manifold lying different orbits of homology or homotopy equivalences, then they're the stabilized one, C1s lying different orbits of these gxy or g tilde xy, where y here is S2. And then in the last step, we want to show that any diffeo of x cross S2 lying gxy, or in the other example, gx tilde y. Okay. So let me tell you about this algebraic sufficient condition. So this step, like the statement in the bracket. So the proposition is let X be a closed smooth manifold with two symplectic four manifolds, the omega 1 and omega 2. If we suppose C1 omega 1 and C omega 2 are in different orbits of action of these homology or homotopy equivalences, of X on your second cohomology classes, because we want to study first-term class, so we only care about the second cohomology class. Then the stabilized symplectic forms have their C1s lying different orbits of action of, sorry, this is just to repeat what I said before, of gxy, gxs2, or gx tilde. Okay. So this one I'll actually give you a full proof because it's quite short, and it's the style of proof that we keep using in our paper. Okay, and it only uses algebraic topology, like grad school algebraic topology. So we suppose for the contradiction that you have such a map in gxs2 or the corresponding one in g tilde x2, such that pullback you pull back the symplectic forms. Okay, let me just complete my sentence for some x2. Then if you look at the pullback of H, so this H is the unique generator of H2S2. And you can think of it, depending on what you like, you can think of it as the Poincare dual of a point, or the algebraic dual of S2, or the first string class of the hyperpolyline bundle of P1. So I want to look at where my map psi pulls back H. So this is this pulls back to H plus alpha for some alpha in H upper 2 of X. I know the coefficient here is plus minus because psi is a homology equivalence, and I know it's plus 1. Okay, this looks like 0 now. I know it's plus 1 because basically of this condition and the fact that psi preserves H upper 2 of X. So psi H pulls back to some H, pulls back to H itself plus some additional cohomology class that's possible in H upper 2 of X. And then we know that psi pull back H squared equal to 0 because this has too high of a degree. then we can expand out. Okay, so h plus alpha square is equal to 0. So this would tell me that 2 alpha is 0 because if you look at the cohomology ring of X cross CP1, which is our S2, this is just H upper 2, H cohomology ring of X adjoint with this H mod out by H square. So now together with this formula and the fact that C1 of P1 is 2H, this is just computation you can do with P1. This gives us, on the one side, we have C1 of the product, so it's C1 omega 1 plus 2H. And then on the other side, we have pullback of the first gen class, which is psi pullback C1 of omega 2 plus 2 psi pullback H. And then you can see that this is 2H plus 2 alpha, which is 0, like this. So we have C1 omega 1 is equal to psi C1 of omega 2. So that we're almost done, but this is a diffeomorphism on a 6 manifold. But we want to, in order to get a contradiction, we need to construct it, a map in GX S2 or GX S2 tilde on the 4 manifold. So how we do that is we just project. So suppose let psi hat to be the projection onto the first coordinate. Then since psi hat preserves 2 of x, we have that the pullback of C1 is the same as the pullback of using the original map, and this by here we know that it maps to the original C1 of omega 1. So right, and then you can check that this is a homology equivalence, or we want to show for both, depending on whether depending on our assumption on psi, this is either a homology or homotopy equivalence. So then we're done. Okay. Sorry, I hope I didn't bore you. Okay, so this is the proposition that we need, that we call it ought to be sufficient condition. Then let me tell you about our counterexamples. So as mentioned before, we have 2 types. I'll first give you the examples by Smith, and then I'll give you the example by Mullen-Taubes. So the one by Smith is a certain fiber sum construction. You consider the 4 torus with this symplectic form. So you do fiber sum with 5 copies of E1s along, in order to specify the fiber sum, I need to tell you where I'm gluing my tori. So Tx, Xt, Ty, that's given by Yt, Tz, T, and oops. And 2 copies of Tw. The exact formulas are not so important, but you should know that Tx, Tw are symplectic submanifolds, while Ty and Tz are Lagrangian submanifolds. So in order to give the fiber sum construction that we usually know, I need to perturb, well, Smith needed to perturb these Ty and Tz. The perturbation actually gives you choices of symplectic forms, and this is what he used to construct non-deformation equivalent symplectic forms on the four manifolds. So his result says the simply connected manifold Z admits two deformation inequivalent symplectic structures. In fact, there's this omega plus and omega minus Z, such that 3 divides one of the first gen class, but not the other. So these omega plus and omega minus, you can think of as choosing different perturbation on, I think, on Tz. So, choosing different perturbation on the symplectic form so that the symplectic form on the perturbed submanifold is now either or agreeing with the original choice of orientation on Tz or disagreeing with the original choice of orientation with Tz. Okay, so these are the symplectic forms he had, and then our job is just to show that they remain non-deformation equivalent. So as I said before, we already have these algebraic sufficient conditions, so we just need to check them. And this is using some information on the manifold Z so that we can study all diffeomorphisms on Z cross S2. So we know that P1, this is the first Pointryagin class, P1 of Z. And the important thing is that this is non-trivial. And it's a Poincare dual of my S2. So since diffeo preserves first Pointryagin class up to sign, because we allow orientation reversing diffeos as well. And just to be complete, and we know the homology is free. So given any psi in div cross S, let me say Z cross S2, in his specific example, we know that psi push forward RS2 up to sign. Okay, now again, it's just some computations of cohomology classes. So given a second cohomology class of Z, okay, we have the psi pullback of alpha is some alpha prime plus AH, where alpha prime is just some second cohomology class of Z. Just remember, we only right. We only know that, well, right now we don't know anything about psi because it's just a diffeo of Z cross S2. We want to prove something about it. So now, right now, it can map to whatever cohomology classes it can, and is, you can see. But we actually know more because if we evaluate alpha with the fundamental class of S2, this is alpha, so because of this we have this is equal to S2, and then we get this, and now we see that this is just A times S2 of this evaluation. So our A is actually 0. And this tells us that any diffio on Z cross S2 actually preserves H upper 2 of Z. And we only really use that the essential thing we use about Z is that its first punctuating class doesn't vanish. So, okay, so this type of proof actually extends to a lot more of examples. And then now we define a similar thing, which is the projection. Well, the exact same thing, which is a projection on the 4 manifold. So P1 psi Y for some S2. And then you can check that by previously, because we already know psi preserves S2. The psi hat has degree 1. And then by some computations, you can check that psi hat is actually a homology equivalence. I.e. this is in GZ. Well, we also showed that it preserves the second cohomology class of Z, so this is in GZS2. And this, so the algebraic sufficient condition is checked. That's fine. So we're done. We know that the stabilized symplectic forms are non-deformation equivalent. Okay. And then as I mentioned in the proof, there's actually, okay. As I mentioned in the proof, this proof applies to other 4 manifolds. For example, the homotopy K3 is given by Vidusi. But this remark says, okay, in my notes at least it says something else. So this type of argument can be generalized to products of Riemann surfaces. This is any symplectic form. Okay, on our specific manifolds. Oh, I have it here, sorry. Okay, so that concludes the description for Ivan Smith's example, which is simply connected. So we disprove the stabilizing conjecture. Before I go into McMullen-Taub's examples, do we have questions? Okay, so maybe let me go into McMullen and Taub's example. So their construction is based on different vibrations of T3, essentially. What they do is you first consider, okay, so maybe first consider the diffeomorphism of L1, neighborhood of L1, L2, L3 between these two manifolds given by zero surgery on the Borromean ring. Okay, the Borromean ring is this K1, K2, K3 component. So that induces you a diffeomorphism, sending the meridians of these KIs to longitude of the LIs here. Sorry, LIs are so L1 and L2, L3, they are geodesics of T3. And then L4 is some geodesic in the class L1, L2, L3. So let me describe the diffeomorphism again. So the meridians of Ki are sent to these Li's. And then you look at this extra component K4, which is sent to L4. So we can consider the manifold M that's that has two descriptions. Either you think of it as T3 minus this four component link or S3 minus this four component link. Okay, and the four manifold they construct is based on is n across S1, where n is the double branch cover of T3 over L, is four component link associated to the homomorphism. The sense, oops. The first three meridians to one. No, where this by J goes over the three, and then the fourth component to -1. And the thing we want to note is that N is also fibered. And obtained from the fibration of T3. And now we recall that the Euler class of a fibration, one description is that, okay, first I need to convince, well, you can believe me that this only depends on alpha, the first cohomology class, and is given by counting sections. Oops, okay. E of given by counting generic zeros of a generic section, where S is okay. I said multiple times there's a generic section, meaning it's transfers to the zero section. Sorry, it may look a little weird because the Euler class here is defined to be in the first homology class, but for the usual definition, you just take its Poincare dual. And now there's this very interesting dictionary between 3 and 4 dimensions given in McMullen-Taub's paper. So I'll copy it here for your reference. So on the 3 manifold level, we have these measured foliations f of them. And then on the 4 manifold, okay, so maybe before that, what is a 4 manifold we're considering? It's n cross S1 in our case. So this is n. This is not a strict dictionary, but it's useful to keep in mind. Okay, so on the 4 manifold, you have symplectic forms. X, and just this is the 3 manifold. N cross S1. And then on the 3 manifold, you have vibrations, where on the 4 manifolds, it corresponds to the integral symplectic forms. And three manifolds, you know that fibers of fibrations minimize genus. And we're not using it here because we're not using pseudo-homologic curves, but it's just for reference that pseudo-homologic curves minimize genus as well. And here is what we use, that on three manifolds, we can consider Euler classes of your fibration. And on the four manifold, that correspond to friction classes. So this leads to their result on, they studied where friction classes are mapped to under diffeomorphisms. Well, they really show more, but in particular, they show that if you have two first cohomology classes induced by two fibrations, such that their Euler classes lie in different orbits of alt pi 1. Sorry, it's not. If there exist two first cohomology classes such that their Euler classes are in different orbits of alt pi 1 of your three manifold. And then they further show that if you consider this four manifold, then one can associate an S1 invariant symplectic form, omega to each alpha n induced by a, let me write it out, represented by the differential of a fibration. And one can associate omega, and you can write down the C1 of this omega explicitly using this Euler class of the fibration. So together with, so this is a 3D, this is a 4D statement. And so together with, by these lemmas, we have that, we can show that for any homotopy equivalence phi of x. This one, it doesn't map these Euler classes, the product of Euler class times S1 to the other one. And so this gives us that if you look at the friction classes, they are also not in the same orbits of homotopy equivalences on the four manifold level. So now we're ready to show that McMullen-Taub's example also gave us counterexamples for the Donaldson conjecture question. And then the information we used about this X, our four manifold n cross S1, is that it's aspherical. So this aspherical, recall that aspherical is universal cover is contractible. Okay, now we use this information to tell us, to help us study all diffeomorphisms or all diffeomorphisms of psi on X cross S2. So let psi be a of x cross S2. And then we have pi2 of x cross S2. This is the same as pi2 of S2, which is just a copy of Z. And psi isomorphism on this. And now by Hurwitz, we know that psi push forward the, okay, I use P1 in my notes, so I just use P1. Plus minus 1 as homology classes. So this is so now that we know that on the homology level it sends one to the to a plus minus of the other, we know that psi pullback actually preserves the annihilator of this, which means it preserves of P1, which means that preserves the H/2 of X. And then we can use a similar argument, almost the same argument, define to be the projection of this diffeomorphism to first factor. Since pi1 of X is the same as pi1 of X cross P1, psi hat is a weak homotopy equivalence because we assume X is aspherical. Oh, we didn't assume. We know X is aspherical. So you have it. Psi is in G X P1 tilde satisfying the algebraic sufficient condition. And note that in this, so we're done. And one last remark is that this argument works for X cross P1 PK as well. So if you stabilize it with PKs for higher Ks, we also know that the symplectic forms constructed in Moment-Top's example remain non-deformation equivalent. Okay, so now I'm done.